Hi, yeah. All right, so thanks a lot for attending last talk in this session, and thanks for an opportunity to speak here. So I'll be telling you about some work we've been doing in active turbulence. So yeah, let me just start off by telling you what active turbulence is. So active matter is basically matter that consumes energy of its surroundings or of some internal energy and converts it into motility. So you can have small active agents that move around. What happens is when you have a dense suspension of these, well, a dense collection of such particles, they give rise to collective states of motion. So that on the left is actually a bacterial system. It's in a swarming state. And you see there's a lot of collective behavior. So there's motion much larger than the scale of the particles itself. And so several of these active matter systems can be modeled by different kind of equations. Here's one such example. It's a generalized Navier-Stokes equation, which very accurately reproduces this sort of motion. So to take you through it, we have you have your acceleration term, you have the nonlinearity with a prefactor lambda. You have terms from pattern forming systems, so there's a higher order Laplacian involved. And at the end, you have a driving term called the Toner-2 drive. And for the purpose of this talk, we actually only need to focus on alpha, which is the activity. So for large negative values of alpha, you're pumping in a lot of energy into the system. So you're kicking up this kind of a flow. And if you have large positive values of alpha, that adds friction. So to this, basically, yeah, so the simulation, the movie in the middle is actually a simulation of this model. And you're looking at the vorticity field. So on the left, you have roughly a velocity field. And if you take the curl of that, you have the vorticity. So you see a lot of these oppositely signed vortices moving around. It's a highly chaotic flow. And to this, we can add tracer particles, which are just massless particles that follow the flow. So it's a very simple equation. And if you integrate this equation out for a particle, you get this kind of a convoluted motion, this long trajectory. And if you average out this motion over many, many trajectories, you get the mean square displacement. So the typical picture is you'll have a ballistic to diffusive transition where at early times, you'll have things going as t squared, whereas at long times, the system becomes diffusive and things scale as t. So this is the rough background of the system that we are working on. What's interesting is that experiments showed that the same bacterial system, in fact, can have anomalous superdiffusion. So what that means is that the exponent of mean square displacement can be between 1 and 2. So it's larger than 1. So things can move much faster. And it has been sort of studied and shown that anomalous diffusion and associated Levy walks and so on, they have some biological function. So they increase encounter rates, they can increase foraging efficiency and so on. So we wondered, why has this not been seen in simulations? And if there is this sort of anomalous Lagrangian behavior, that will also manifest in other Lagrangian measurements, which has not been shown. So we wanted to study this. So I just want to start by showing you what happens to a bunch of tracer particles in these kind of flows. So here will be simulations of mildly and highly active turbulence. That's the background flow, which you don't see. And in that, we are putting a drop of tracers, basically. And I've colored them with yellow and blue just to show you how mixing proceeds in such a system. So on the left, you'll see that that's mildly active turbulence, the first movie that you saw in the first slide. And the tracers immediately pick out all the vortices, very nice sort of a diffusive motion. On the right-hand side, the motion is very different. There are several new things that are happening at high levels of activity. The first is that you see there's more multi-scale motion. So you have larger vortices, smaller vortices. And you also see that there are some material lines like this one. They just propagate in a persistent manner. They don't deform for a while. And then suddenly they will twist and break. And then you'll have another material line that moves persistently. So clearly there's a very big difference in the Lagrangian picture at mild and high levels of activity. So something is changing as we increase activity in the system. So we want to quantify this, of course. So we look at the mean square displacements for increasing levels of activity. So the arrow there shows you increasing activity. So as I told you, at low and mild levels of activity and in values of friction, you'll have your ballistic to diffusive transition. But at very high levels of activity, you get a very robust super diffusive regime, which goes of t to the 4/3, and that's over 2 decades in time. So clearly there is anomalous diffusion in the system. Now, the question is, can we quantify this a bit further? For that, we need to look at the trajectory separately. So here's just one such trajectory, which we've segmented into what are known as walking segments. So you just mark out the turning points in a trajectory, which is a fairly trivial process. And each color gives you one walking segment. So you have a waiting time distribution. So that's time between successive turns. And you have a step size distribution, which is the distance traveled between successive turns. And we want to look at the distribution of this because that's what really helps you characterize the nature of these trajectories. And if you plot out the, let's say, the waiting time distribution here, then it follows a power law distribution as well. And this happens over few thresholds on this turning angle criteria. The main point here is that the exponent that we get from the waiting time distribution, together with the exponent of the anomalous diffusion, they together tie up very nicely within numerical errors to what comes from Levy-Walk theory. So we can say that actually bacteria are performing Levy-Walks, and that's why they have anomalous diffusion. So that's the first Lagrangian anomaly in the system which we could confirm. So clearly this will have repercussions on other measurements. So we wondered, what do these trajectories look like? I mean, do you have a very persistent segment in a trajectory, and then there's a diffusive segment and so on? So we wanted to visualize and quantify those aspects. So what I'll show you here is, this is just a collection of the fastest and slowest 1% of the trajectories to reach a certain target radius. Now you can imagine that they start in all sorts of different locations in the flow. So we artificially bring them to a common center, and we let them flower out to this circle. And that reveals something very interesting, actually. What you see is that the persistent trajectories, they show a lot of bundling. So there might be this blue bundle here, so the trajectories look similar. There's one towards the left, they look similar. And you see these long walking segments that are very straight. So there is clearly persistent motion, and there is some kind of selective sampling in the flow. I mean, these clearly must be happening at nearby points in the flow. Otherwise, you will get very different looking histories. So this gives us an insight on how these are distributed in space and what's the nature of these trajectories. The diffusive ones, they just meander for a very, very long time, and they take long to reach this circle. Now, what actually happens is that there is no such thing as one trajectory that's persistent forever, one trajectory that's diffusive forever. There's a mix of both. This will give you more or less ballistic movements. This will give you purely diffusive movements. And hence you get an anomalous scaling exponent. And this exact picture can be quantified more with the first passage time distribution, where you ask the question that if you have circles of increasing radii, how long does it take for a trajectory to reach that circle? So for different values of r, we can look at distributions of the reaching time for trajectories. And as you would expect, well, naturally the distribution widens over time, because once you have a very large radius, let's say 30, you take more time. But if you scale things by r square, this is for a mildly this is for a mildly active system, then these curves collapse because the motion is mainly diffusive. So you get diffusive scaling here. But what happens when you have very highly active turbulence is that you get two scaling regimes. So for relatively small target radii, like suppose here, your trajectories are dominated by the persistent motion. So you get a collapse with an anomalous exponent. And at long times, again, things will obviously become diffusive. So things go back to your R square sort of a collapse. So that's another anomalous Lagrangian feature. And we found these consistently for other measurements, like in pair dispersion. And actually, whatever Lagrangian thing you look at, this will sort of play a role at high levels of activity. So far, what we found is that increasing the activity changes the Lagrangian picture. Then the question is, does it also change the Eulerian picture? What's happening to the fields themselves? So I want to show you here, again, the left-hand side is just a movie of mildly active turbulence, which you saw earlier. On the right is a very highly active turbulence. This is the vorticity field again. So positively and negatively signed vortices. So on the right, you see, again, there's a lot of multi-scale motion, large-scale circulation is going on, very different behavior. But what's interesting is that if you look very closely at these fields, you also see these banded streak-like structures, which are not there at mild levels of activity. So here's just a snapshot. So if I zoom into these kind of regions, for mildly active turbulence, you just have spherical spots of vortices, whereas here you have streaks as well. And what's interesting is that the local streamlines, they seem to align in a persistent manner in the streak regions. So the obvious question is, do the streaks aid in persistent motion? Because high levels of activity on the one hand gives you Lagrangian anomalies and anomalous diffusion. On the other hand, gives you Eulerian streaks. So are these responsible in some way? So the first thing we need to do is come up with a criteria to identify streaks, because they are embedded in this sort of a field. And these are geometrical shapes, as you can see, they have a certain dimension. So you need a criteria to be able to pick them out. We came up with an ad hoc criteria, which works somewhat robustly to give you these streak regions. What that allows you is it gives you a point-wise measure of whether you are inside or outside a streak. So now if I take my trajectory, I can color it with, let's say, red and blue, where one of them means, okay, now I'm in a streak region, then I exit it, I'm outside, then I again enter a streak region, and so on. So with that, I can look at a joint distribution of residence times in the streak regions with a normalized displacement, and residence time outside streak regions with a normalized displacement. So the first thing you note is that this is a very small figure because the streaks are, let's say, 10% of the volume. So you don't have a lot of residence time there. But interestingly, the curve is much steeper here. That shows you that the displacement that you're likely to have in a streak region is much higher than outside of a streak region. So we can conclude that the streaks do aid in this kind of persistent motion. Yeah, thanks. So I just want to give you a glimpse of what we are doing now with this system. So we are looking at other questions like intermittency and fluctuations in this system, chaos, universality, and also some experimental follow-ups. So for instance, there has been this very interesting and very seminal paper which showed that in the same model that I showed you, there is actually non-universal spectral scaling. So if you increase the level of activity, your spectral slopes become shallower and shallower. So you see you move in that direction. And there's a linear relationship here. So they said that the scaling is non-universal. However, what we find is that if you really move to large levels of activity, then first of all, well, you can reproduce this linear behavior, but then there seems to be a sudden sort of a phase transition to a more or less constant spectral scaling. So it could be that there is asymptotic universality in the energy spectrum. And the exponent is quite reminiscent of this Irashnikov-Kryknin kind of energy spectrum. But at the moment, given the accuracy of our data, it's hard to distinguish 3/2 and 5/3. The numbers are very close. So we are looking into this. The other thing that we are doing is we started trying some experiments at NCBS. So Shashi has been very kind to invite us to his lab so that we can use their systems. So here's Martin, one of our collaborators. He has a very changed environment now. So another thing we had to do was change our vocabulary, which went from everything in programming to the real world. So now we are dealing with pipettes and glass slides. So this is a very recent experiment from 2 days ago of wild type E. coli. And if you recall the first movie you saw in the first slide, this sort of resembles that. We are still not sure if this is in an active turbulence phase, but it's clearly swarming. So we want to reproduce some of these results here, see what the real system is doing as well. So yeah, that's basically the talk. And the summary is, I want to end with this quote, which is, if you want to go fast, go alone. If you want to go far, go together. That's because bacteria actually go far by going together. It's this emergent flow of the system that gives rise to this beneficial biological motility. Individual bacteria can't do this. So it's really a collective motion that's at the heart of this phenomena. And I'd like to end by acknowledging Rahul Singh, Martin James, and Shomriddhi. We worked on this together. And the experiments at NCBS, I especially want to thank Suresh. He's a student of Shashi. He's been helping us a lot with, I mean, we have never been to a lab before. So it's very kind of them and very patient of them to teach us all these techniques. So yeah, I'll end there. Thanks a lot for your attention.
We have time for a few questions. So,
hi. So in the plot that you showed for MSD, what happens when the turbulence is inertial?
It's ballistic to diffusive.
Ballistic to diffusive.
So if you increase the Reynolds number, you can change the diffusion coefficient, but the exponent does not change in regular turbulence.
So you don't get that intermediate regime.
Or tracers.
Okay, and like how high your activity should be in order to get this anomalous sort of behavior?
So the activity number here is, let's say, -6. What that corresponds to is your average bacterial speed, which might be, the mean of that is, let's say, 20 micrometers per second. An equivalent of this activity would be, let's say, 80 micrometers per second. That's roughly, I mean, just to give you a physical intuition for what this number means.
Okay, no, I was wondering, is the something that sets that time scale, like beyond which if you go, you get some anomalous kind of behavior.
Say that again, sorry.
I'm saying like, is there any time scale in the problem?
The activity sets a velocity scale, so you can get a time scale out of that as well.
No, if you go beyond that time scale, then you get this anomalous regime.
I mean, if you correspond that velocity scale to a time scale, then you can argue along those lines, I think.
Because for small, I mean, alphas, I mean,
yeah, small alphas you don't get.
That was not there, yeah.
Yeah.
Yeah. So I was just wondering, in the experiment you're doing with these bacteria, like what observables can you measure to compare with your model?
Yeah.
Like, how do you do this? I mean,
so the idea here would be to seed this with tracer particles that fluoresce. So when you shine an LED, typically a laser, but an LED would work as well. So then that's going to fluoresce in a certain band. And then you measure the tracer particles and you convert that using particle image velocimetry into a velocity field. And once you have the velocity field, then you can go back to numerically putting tracers into it and doing all sorts of statistics. So we just basically want to get a velocity field of this system and maybe get the tracer motion as well. That's the information we'll get from the experiments. And what will vary is things like the density of the bacteria, their motility, and so on.
I see. Okay, thanks.
In the Navier talks, you added this sort of nonlinear dissipative term, and then there was a del 4 term, and then you said that lambda not equal to 1, right? Is that also crucial? Like, I mean,
so that's a good question. I mean, there are a lot of parameters here. The thing is that if you there's an entire phase map for this equation. What all can you simulate? So you can do active turbulence, you can do vortex crystals, you have steady states as well. And large scale condensates. So lambda is one of those axes. So if you vary lambda, you might go to a different regime. So we have to keep lambdas mapped to experiments such that we are in an active turbulence sort of a phase.
So lambda 1 wouldn't give you all this.
Lambda 1 without changing the other parameters, probably not. But if I also change the other parameters accordingly, maybe it still gives me that. So but lambda 1, I think, might actually still give me this thing. I mean, I'm not sure yet, but yeah, if you vary it a little bit, it's fine. But if you vary it by a factor of 10, then you might end up in a different regime. Yeah.
If there are no further questions, let's thank Siddhartha again for the great talk. And